He has almost 10 years of experience. Rohit MR, you can add one more time. So still people are coming. Let's see. Yes, if possible, no, if people turn on the videos, no, I want to see, no, how many people are actually listening. What you can do, after half an hour, no, you just turn on your videos for some time, and you'll see, whether you people are actually listening or not. Understand? Don't know what is happening is, we'll be teaching. But I told you, these three companies, ma- many companies are there. Many companies are there in Bangalore. Only, initially getting into these companies will be very difficult. But once you get into this companies, it'll be very good. And you can see this, top 20 VLSI companies are there in India, Bangalore. Top 20 means these are the top 20. This is top 20. All Intel, Texas Instruments, IBM, every R&D are there in Bangalore also. And he was telling you, see, fresh graduates are not skilled and industry ready. Obviously, we don't have that much skill. Now also, if we ask, digital electronics basics, it'll be a little difficult to get into, like actual, core companies. And we should have the strong CMOS and digital fundamental. That's what, like he told that day. Because if you're good in this digital fundamental and CMOS, then things will be easy. That's why now, whatever the companies are there, majority of the companies they'll go to this IITs and NITs. They'll take B students also, but majority, they will directly take fresh graduates of MTech and MS. They'll offer internship. You need to work over there. If you're they are satisfied with your knowledge, definitely they'll observe. So you need to plan this way. Either you need to do, if you want to get into VLSI, nice project you need to do in this duration only. You can plan your projects now only. We have this high-end tool. They don't want a complete. You should know the entire thing. If you can show them that no, you can do it, then no, they will be in a position to take you. You should have that stuff. So that no, you should have this basic fundas. Wrestling need to be strong in CMOS and digital fundamentals. These are the things. And this is the VLSI flow that day they spoke. This is a general VLSI flow. Yeah. RTL engineer is a function and verification testing engineer is a. Here also one domain synthesis. FPGA also people will work on this domain. Different physical design also one domain is a. People work on physical design. Then testing, verification, RTL description, FPGA implementation. Many people will be working on different this one. If I just Google it and you see now also you can see VLSI. Openings in India, instead of Bangalore, I'll make it. You see, now Google only is giving you some. See, in Bangalore, this is the first search. See, I'm just telling you. Will I say openings in? You can see, Bangalore, Hyderabad, Chennai. So many, options are coming. So you go for Bangalore only. You can see this. This is the actual now also this one is there openings are there. You can see physical design engineer. This is the best. Even I'll also like this physical design engineering. And you can see this one. uh, this is for how many this one is asking as a part of, see, they'll be working on this 7 nanometer to 16 nanometer physical verification. Also you need to do block and chip level. They need to do good knowledge in VLSI process design characteristics to make the optimal trade-off between performance and power. Good knowledge and standard cell libraries. All these things are important actually. And he's asking, prior experience in 16 nanometer technology and good software and scripting. Zetical actually, once you get in, the software and all, it will be easy. You see, 2.5 lakh to 2.7 million per year. This is the nature of work actually. See, job location in Bangalore. See, Wipro also they are called. Wipro VLSI also, this one is actually DFT, designed for test actually. This is testing jobs. And so people are coming, 18 people have joined. Okay, let them join later. We'll see this one. No, last class, I spoke about this Manchester carry chain, where you need to use this generate and propagate concepts. So when clock is zero during the pre-charge phase, like PMOS is on, NMOS is off, your Cout will be charged to logic one. This is called pre-charge phase. When PK is one, this PK is one means is a propagate is one. PK is one means AXR B is one. If any one of the input is one, whatever there is the carry, it will go to carry out. GK is A bar plus A bar dot B bar. So GK, if both are 0 0, so this will be turned off. So previous output whatever is there, sorry, GK 0 0 means A bar will become one, B bar also will become one. This GK will turn on and it will discharge. So you'll get logic 0 the output. If GK is 1 1, so this GK will be off and logic 1 will stays there only. This is the Manchester carry chain. That's what we have seen in the previous class. And this is the cascading of carry Manchester carry chain adder. So as a cascading of Manchester, this one cascading Manchester carry chain. Second, that's why P0, P1, P2, P3, G0, G1, G2, G3. So we were cascading our carry adder. Then in the adder enhancement, we have this three adders: carry select adder, carry skip adder, and carry look adder. Now, first we spoke about carry select adder. In the carry select adder, so you need to select before actual, like sending into full adder. Full adder can take either logic 0 or logic 1. So add full adder with the logic 1 and logic 0. So whatever the results is, you just select through your mux. Mux will select the data which is already computed. It's like all these full adders will compute parallelly. So data will be ready. So based on the mux select line, based on the carry, so one of the data will be selected and will be processed to the next block. That's why you can reduce your delay. And the total delay is this one. So we'll be dividing our carry select adder into blocks. So here in this case, this is one block, so we can take this the actual diagram. So here in this case, we need to select into blocks. So this is one block, this is one block, this is one block, and this is one block. Three blocks are there. Here M is 3 and P is the number of adder cells in each block. So three blocks and two adder cells. So at a time now, as I told you yesterday's class, at a time now only one of the full adder will be working. So only two full adder will be working at a time, because based on the carry, either you will select this full adder or this full adder, right? If carry is 0, so this one will come. If carry is 1, this one full adder will be selected. Then based on this, data will be moved. So this is the equation. So three blocks are there. So P into K1, P is number of addresses is 2. In each block, two addresses are there, 2K1 plus M minus 1. So total M was number of blocks is 3, 3 minus 1, because first block, we don't have mux. That's why it is M minus 1 into K2. To find out the minimum value of T, so you need to differentiate this with respect to M. There is M block. So you'll get M is equal to N into under root of M K1 by K2. So under root of N into K1, N is number of bits. So this will be getting this delay. Any doubt? This yesterday, if you have gone through it, any doubt? This is not carry skip adder, this is the carry select adder. carry select adder. It should be carry select. We are selecting the carry. So next one is carry skip adder. Into carry skip adder. So as yesterday I was telling, you will be skipping the entire block. You will check this propagate and generate. This is the computation A5 XOR B5 and A4 XOR B4, so on, A0 XOR B0. So that will be considered pi into pi. You check this bits. If any one of the bit is logic 1, or like if A and B are not equal, then this pi into pi will become 1. So directly you pass the carry out. You don't have to do computation, or you don't have to do addition of all the bits. You directly skip that block and you can go to next one. If it is equal to 0, then you do normal addition operation. Then you send your carry out. Right? If this is 1, you skip the block. It is not equal to 1. Or if it is 0, you do normal computation, generate carry, then you send it to the next stage. That's what it's carry skip adder. We are skipping the blocks. We're skipping the blocks. The worst case propagation, what he has done is he has taken p into pi is equal to 0. Here also it is 0. Now in this case, as it is 0, that means you need to do addition. You add all the bits, AI and BI up to 5 bits. You need to add whatever the carry is generated. That carry will go through this marks. Your pi into pi is 1. It will skips this entire block. You don't have to compute again. Here also it will skip. When you go to last block again, here there's no computation. You need to do this normal addition. This is the delay of C23. This is worst case delay for carry skip adder. What we have done in the last class. Now the last adder, this is carry lookup adder. As I told you, in yesterday's class, there's a comparison table. We have different adders. In that we have learned only repel adder, carry look adder, I'll be explaining this carry look adder, carry select adder, carry skip adder. You can see this carry look adder will have less delay, 0.72 nanoseconds compared to other, like uh, repel carry adder, carry select, and carry skip adder. Obviously, it has its own advantage, because all the time, you cannot skip the block, because the data, whatever the data you want to add, it won't be not equal. It's like A always we cannot predict always A and B are not equal to not equal. So that's where the problem will come. But majority of the cases, if it is not equal, you can skip that blocks. So that's where delay is 0.87. But in carry select adder, because we know the carry can be either logic 0 or logic 1, right? That's why the delay is less, right? The last one, you can see carry look at adder, it's taking only 0.27 nanosecond, 0.72 nanosecond. Why? Because of these things. Now what we'll do is carry look at before actual computation, your carries will be ready. Before actual computation, your carries will be ready. So in a way, your entire design will become faster. So you can see this is 16-bit carry look at add circuit. 16-bit because this is 4-bit, S0 to S3, then S0 to S7, S4 to S7. So you may S15 to S12. So this is a 4-bit carry look at that. Again, what will happen is, imagine, okay, come back to this one. What is the drawback? You see this is the equation we'll be using. C0 is equal to G0 plus P0 into Cin. This is a simple equation, already you know this. So here G0 is A dot B. So I can write this equation. I'll write here. So I'll take this. So this is G0 is A0 B0. This is A0 B0 plus whatever the concept till now we have discussed is the same thing. P0 is A XOR B0. This is A0 XOR B0 into Sin. So this is the equation. So C0 is equal to G0 plus P0 into C1. I told you, If both are equal or both are equal, A dot B. A dot B means no AND gate. If both are logic 1 or both are logic 0, it's like and both the conditions should be satisfied, right? Same way, if both are logic 0 or both are logic 1, new carry will be generated. That's why it's called G, generate. Then P naught, propagate. If any one of the input is logic 1, if any one of the input is logic 1, so you'll get carry will be propagated. Carry will be propagated. That's why it's called P naught. So P naught into C1. Using this scene, using the scene, so you can generate C1. C1 I can use this way. C1 is equal to G1 plus P1 into C naught. G1 C1 is equal to G1 plus P1 into C naught. Using C naught, what is C naught? C naught is nothing but this, right? So you can write this. C naught is G naught plus P naught into C n. If you multiply with this, so it will become G1 into P1 into G naught plus P1 P naught into C n. So this will be your C1. Same way you can generate your C2. C2 is G2 plus P2 into C1. Again, C1 is this. You multiply with this, you will get C2 as this. This is C2, again C3. You see, with the help of only Cn, with the help of only Cn, you can get back your C3. You can get your C3, right? You don't have to wait for C1 or C2. Directly, if you know Cn, you can directly get your C3. This is the basic concept. So this is how your circuit diagram looks. You see, there is a separate block will be there for your carry lookup adder. You just keep this C0 and this input. Your all this S not S sorry C1, C2, C3. How many carries you require? Everything will be generated in the circuit. Based on that, it will give you. So this is a carry lookup unit. You leave this G1, G2, G3, G4, G5, P0, P1, P2, P3. It will get C1, C0, C3. All the carry will be generated easily. The main drawback is, imagine, again, here also, you cannot directly use, you just take this equation, you build the circuit. This is for C3. You see, so many equations are there. G3 is, A3, B3 plus P3 is, A XR, A3 XR, B3, the G2 is again A2. So many equations will come. Imagine C100. C100, if you want to build your circuit, building that carry lookup adder circuitry only becomes complex. Area you require is more. So in a way, you're getting best delay. That means, your speed will be very high, but it will consume more delay. Imagine, you have mobile phone, or you can take, iPhone 10. It is very fast, but no, it is the size of laptop. Can you able to carry your iPhone 10 everywhere? How you are carrying your laptop? It's difficult, right? So that's why you need to make sure you'll get better performance. For that, what they will do is they will design like this. For 4-bit, they will use this carry lookup adder. Again, that next carry will be given to this. It's like it's combination of carry lookup adder. You see this, if n number of adders are large, the carry output bits increases. Obviously, it will increase, and the expression longer and complex. I told you, area will become more. Obviously, expression will become more means, imagine this is for C3, C100, right? So many, this one will be there. G99, then P99 plus P98, G98 plus so many, this one. Obviously, area required to implement will be a little complex. Thus, carry lookup adder and rebel carry adder club together. So we can club or carry lookup adder and triple carry adder. This is a carry lookup adder. So for 4-bit, then carry will be propagated to next stage. There's rippling, C3 is rippling from this block to this block. Again, there is a 4-bit carry lookup adder, and again carry, right? Again, this one is there. Again, we can do. We can make it for a 4 bit is you can make it for 18 bit or 16 bit. You cannot go beyond 32 bit because area required will be more. Obviously, you'll get since you're before actual competition, no, you're getting all your carries ready. C1, C2, C3, everything will be ready. Just take the data and compute. That's why from this equation you can see this delay is very less compared to other things, 0.72, and you can see ripple carry added almost is 2.04 nanoseconds. It's a huge delay, right? And you can see this one again to increase the speed. What they have done is C3 is equal to S taken, C3 is equal to gamma plus pi, gamma plus pi, where pi is P1, P2, P3 same, and gamma is G3 plus P2. It's similar to your this one, only difference is here. You see what you have done is GIPI, these are your input, generate plus propagates inputs you'll give to calculator. C0, C1, C2 will be generated. C3 will go to this pi naught into gamma. So pi naught into gamma is nothing but this. This is generate and propagate only. Simple. You give this to over here, and C3 will go to next block. C3 will go to next block. It's a simple concept. This one only. Whatever you will learn, you take this 4-bit, you generate the carry, and carry will be propagated to next block. It's a combination of carry look added and this one. So that's what you are doing. You give this again. You generate C4, C5, C6, C7 will be from here. Go there, compute. Again you come back, give here. Again here, and finally you'll get C5. It's the same thing. 16-bit, 4x4 block carry look added. That's all. It's a 4-bit. So this completes your module 3. Is any doubt? Is any doubt? You can turn on your mic and you can let me know. Any doubt? Is any doubt? Priyanka. Is everyone turn on your videos? I want to see whether you people are there, actually are there or not. Hello? Is any doubt?
No, sir.
No, sir.
His strength is very less today. No doubt is there. All the circuits. Nothing is there? Okay. The module 3. You need to go through these things. Then only you'll understand. This is not that easy. You need to spend some time. Then only things will be easy. Understand. This will be a little difficult if you don't understand. If you understand, the subject is very easy. If you feel little difficulty also, if you don't understand, you cannot mug up this layout, these circuits. If you know the concept, then only you can do it. Okay. This is module 4. Again, this is the extension of your subsystem design. Is a subsystem design and FPGA based system. This is the module 4 of your syllabus. This is the extension of this. Even here also we'll be learning about some subsystem. So that's what he's telling. This deals with designing a subsystem with a smaller part of your larger system. That's what I told you. Will be we took ALU. That ALU, actually multipliers also is there, but multiplier we will not learning. So that they are not kept in our syllabus. When you take ALU, all the logical units, everything is there. Multipliers, adders, subtractor, and all the logical expression. But, in our syllabus, what we have done is, we are mainly concentrated on adders. Using adders, you can build all the logical expression, addition, subtraction, all the logical expression. Then we have seen different adders. Multipliers is not there. Even different multipliers are there. That we have not seen. That's not there for our syllabus. The next topic is subsystem design and FPGA. That's what he's telling. And the most basic leaf cell of any digital system is logic gates. Obviously, your all your AND gate, OR gate, NAND gate, XOR, all those things will come. You can implement all the gates using this N logic, NMOS logic, CMOS, BiCMOS. Again, based on the application, you can go for NMOS, CMOS, and BiCMOS. We'll see all those things. So these are some of the architectural issues. When you're designing something, you need to consider this thing. What we need to do is, first you need to take the requirement. You can see this, the flow. So you need to follow same thing actually. There'll be a specification. Based on the specification, you need to write the code, that is RTL description. Then you do this verification. Obviously, whatever the code you've written, whether it's meeting your requirement or not. Then you try to optimize your design. You do this synthesis. Synthesis is nothing but converting into gate level netlist. It's like, your big expression I told you, right? CAD look at, you're using so many gates, so that is not required. Generally when you write code, the if loop, for loop, all those things, it is not optimized. We need to try to optimize our code so that we can fit our IC in small area. So synthesis is a method where it will convert your HDL code into RTL at the gate level netlist. At the same time, we'll try to optimize your design in terms of area, power, delay. Then comes your backend design, where you will do actual layout. We have learned the stick diagram of the layout, right? That's what we will be doing in this physical design. In the physical design, you require library, then logical library, physical library, and the technology file. Which technology you're using? So we have seen this Lambda rules, right? So that Lambda rules can be applied for different technology nodes. So this is a technology file. So 45 nanometer, 18 nanometer, 14 nanometer. So based on the company requirement, you'll. I told you, right? You see this. Just now I googled it and I showed you. Some companies are working in this one. The previous company, they were working on this. This is a physical design engineer. You see, this is the job profile. They're looking for this. And this, you see, this 7 nanometer or 16 nanometer process nodes. Process node is nothing but your technology node only. That's what we are discussing here. We are talking about this. This is a technology file. So physical design, you see the input is technology file. So this is job profile of physical design. So there they require this 7 nanometer and 16 nanometer process, this one. And you see, good knowledge of EDA tools like Synopsys, Cadence, Mintech graphics. These are the like EDA tools. EDA is electronic design automation. Then sign off. Sign off is nothing but where you'll do actual verification in times of testing, in times of actual layout. Everything will be doing. Then you will send it to fabrication. Again, in India, fabrication facilities are not there. Mainly, in China or Taiwan or US, where you'll be sending, US factories. We have this Intel is there, AMD is there. So many, fabs are there. And finally, you'll do this, right? So same thing. Those are the general architectural issue. Define the requirement carefully and properly. Obviously, you need to see the requirement. What exactly is the requirement? Then partition the overall architecture into subsystems. Again, you need to build your mobile phone. You need to partition. It's like you not build the entire mobile phone in one person cannot build the entire thing. So someone will be working on poster. Someone will be. Let's say you see like Apple, they'll just assemble it. They were given contract to different Chinese people, companies. So you see Broadcom will be there, like then they own the processor is there. So different company. If you see some other company like MI or OnePlus, they'll be using Snapdragon. They'll be using then Samsung. That display they'll be using. Processor is different. Keypads are different. Touchpad is different. Different vendors. They'll be working on separate subsystems. Right. The processor is a separate subsystem. Then communication between processor and the other hardware is one system. The display is one system. So then all the calls, whatever no GSM or whatever the technology they'll be using, that is only separate subsystem. All those are separate. We need to divide. Then communication path should be carefully selected in order to develop sensible interrelation between the subsystem. Obviously, when you take, you're buying different components from different companies, and we need to make sure everything will work together. It's like, you take this Snapdragon processor, and if it is not compatible with the Android, what is the use, right? The Snapdragon and your OS should communicate with each other, and that in turn should reflect in your display, right? Draw the floor plan, how the system is to map on the silicon. Obviously, you need to utilize floor plan is nothing but it's like, construction of your rows. Some 30-40 site is there, so we need to make sure how best we can use, where my kitchen should go, where my dining hall should go, where my bathroom should go. Everything you need to plan. Whatever the small areas are in Bangalore and all, like where site is very costly, so you need to you need to make best use of our site. Same way, whatever the IC area, the silicon area we are getting, in that we need to plan our components, where exactly my power grid should go, where exactly my already verified data, the design should go. So where I need to place my components, how exactly each component should communicate. Everything you need to plan in this floor plan. So can will you know it is not there. Floor planning. You can see this is a floor plan. You can see this. See this images. Yes, it is proper. No, yeah. This is only floor plan. No, you need to plan your components, how you want to place. See floor plan from microelectronics. I see. Oh, all the components. You can place. These are all your like area. ICC log is your transistors. You can see how each block you need to place. That's all. No, it's only floor plan. Yeah, but the slide I'm not getting. Yeah, you see, you can see this one also. This is also one of the major this one floor planning. Here they are placed. I can see here. This also you can see different. This is a layout actually. This is a floor plan. All these things are your pads, IO pads. All these things are IO pads. There's a VDD. There's a ground. Then there is a ring oscillator counter. Is there 4-bit counter, then 2-bit counter, then single inverter. This is the planning. Actually, they have placed this component, but before that, they need to plan how much area is there, where my VDD should go, where my VSS should go. All those things you need to plan. This is the like final product. It's like after placing, after doing interconnection, they have got this circuit actually. These are actual components. They are placed. You see, this is how your core area looks. This is the final IC. Photo. This is the back side. No, this is the front. You can see this is how it will be there. These are all pads, the IO pads at the input. From here only actual metals will come out. Aluminum metals will come, right? These are all your pads. Then you can see all your metal traces. Inside your IC, it looks like this. Inside your IC, this will look like this. Finally, this is the end product. That's what we'll be doing in your lab. Actually, in VLSI lab, whatever we are using in Cadence, we can do entire thing. We can design these things. You also can do manually. Everything it's available. Only thing is, you need to work on these things. draw the floor plan and how the system and mapped on silicon. Aim for regular structure so that it largely matter of application. Obviously, no, when you design something, you need to make sure no same you design best AND gate. So same AND gate you can use for different application. Or imagine you're using carry look adder. You're compared ripple carry adder. You compared carry skip adder. And you've done everything. You based on your requirement. You don't want to compromise with area. You don't want to compromise with speed. You checked which one is better for your application. You can go for carry skip or carry select adder or carry look adder. You're choosing that one, and once it is ready, so you can use that look add adder or carry skip adder whenever you require. So that's why it's aim for regular structure so that design largely a matter of replication. So it is not like that, okay, like for me speed is really important, I'll go for carry look add adder. You can generally you can do it, but you cannot use whenever where area is not concerned, right? Then draw the suitable stick diagram. Then convert the stick diagram into layout. Carry out the design rule check (DRC). We'll use that lambda rules, right? That polysilicon to diffusion, 1 lambda spacing should be there. Metal 1 to metal 1, 3 lambda spacing should be there. All this rules you have done it, right? So we'll be checking those things. So design rule check. So once your design DRC, we call this as DRC. After that, we'll check ERC, electrical rule check. Then we'll do parasitic analysis. Of once everything is done, then only we'll simulate the performance of each cell or subsystem. Right? Once your DRC is fine, then only if your DRC, if you won't follow your DRC design rule check, then the entire system will be wind up the wrong system. You cannot use this. You need to make sure all these things will be followed. So many times they've asked us explain the architectural issues followed in VLSI. So that time you need to explain all these things. This is very important. So many times they've asked questions on this. Next one is we can design MOS in different way. It can be switch logic or gate logic. Gate logic or restoring logic is nothing but normal gates, AND gate, OR gate, the XOR gate, everything you can build using NMOS, CMOS, and BiCMOS. So the basic building block is first one is inverter. First one is inverter. Yeah, this one is NMOS inverter. I hope people know layout, right? Layout and stick diagram. You guys are comfortable with the stick diagram and layout. Again, here also so many like circuits where you require stick diagrams. Stick diagram and layout you'll be using. You need to make sure whatever the previously you learned the stick diagram and the layout, you should be good in those things. You cannot mug up stick diagram and the layout. You need to understand the concept. Accordingly, you need to build your circuit. If you don't understand concept, it will be very difficult. Clear, guys? So everyone is comfortable with stick diagram and the layout? You need to answer me. If you're not comfortable, I need 1 or 2 classes to explain you stick diagram and layout. I heard like Shurudra sir was telling he has given I have not seen all your assignment. I've seen 1 or 2 like I don't know, like I heard someone has taken from internet, so same thing you people have copied. That's what I got it. You should not do it like that. This subject is, it can be easy, it can be very difficult subject. Question paper can come very easily. It's like direct questions. If you refer to your 4 or 5 years question paper, can easily score above 70, 80. Again, you can set your like question paper can be set in different way also. So if like the professor is like very good in this MOS and I want to test student, he can set very difficult question paper also. You cannot answer also. So that's why I'm telling you, you should be no concept wise. If you're clear, whatever may be the question, you can do it. If you're not able to do, then it will be very difficult. Yes, tell me, how is your like stick diagram and layout concept? You should be frank. Then only I can do, because so many stick diagrams and layout will be coming. I'll just run through this. You see, this is stick diagram. Mainly, we'll deal with stick diagram only. So many stick diagram will be coming. You see, AND gate, OR gate. You see, this is a BiCMOS NAND gate. You cannot mug up this one. You see, this is what? No, this is the AND gate only. So you cannot, remember this circuit and go and do. No, you cannot do. You should have proper concept. Then only you can do. Okay. So tell me, frankly, do you want me to repeat stick diagram and layout? Yes. Yes, sir, there. Okay, I'll assume now if people know the stick diagram and layout, so directly I'll go. So that's why I told you now. After that, I won't explain. You need to understand. You need to do it. This is the inverters. This is the simplest inverter. This is the NMOS inverter. Then this is BiCMOS inverter. This is CMOS inverter. So this is the circuit diagram. The NMOS inverter always will be using. What is this circuit? Can anyone tell me? So can someone can unmute and tell me? Let me check. Who is all in light? 33 students are there. Tejas. Tejas, you're there. Tejas Kumar. Tejas. Then Vadiraj,
Yes, sir.
you're there.
Yes.
So can you tell me what is this circuit? This one.
So, so invert that
This
was.
only this gate.
So, um, so
Check
that
this.
is.
Tell me. You go ahead.
So that uh, PMOS.
You must. Tejas is not there. You just turned on the, like you just logged in and you went off. Huh? Vivek. Vivek. Vivek Prakash. You're there. Vivek.
Yes, sir.
You're there. Okay. You tell me what is
Hello,
the circuit? Yeah, you tell me what is the circuit? This one, only this gate.
sir. Actually, I'm attending.
Huh?
Sir, which one? Sir, PMOS.
PMOS. It's not PMOS.
Hello,
Why you did not attend all stick diagram and layout classes?
sir. My connection is not good, sir. I'm somehow managing here. It's like 30 kbps max.
Okay.
Hello.
Yeah. Okay. But you should know, right?
Yes, sir.
Oh, Sushma. Where is Sushma? Sushma. Sushma. She's there. Yes, I don't know. Like only for namesake, if you log in, then it doesn't make sense. You see, now people are logging out. Huh? 32 was there. Now, no, 3 people have left. Sushma, you're there. No. Yes, this semester, no, everything will be online only. So you should be careful. Sahana, AK.
Sir,
Yeah, tell me what is the circuit?
yes, sir.
This gate.
Sir, excuse me, sir.
Who is this?
Sir, we got some different link. We have been trying for that link, sir. We actually missed the class, sir. Some of us who joined recently.
How come?
Yes, sir.
How come I have sent the only one link? No.
No, sir, we have been trying the link what we got for mail, but it was not the actual one, sir. There were people in that, and we again got a new link, so again we joined it, sir. After almost like 20 minutes.
Yes, sir. Some of us.
So can you, if you don't mind, can you explain, sir? We missed it.
No, just only carry look at other started. This is the
Okay,
basic.
sir.
This one only. This is the beginning of class. You see, in the
Okay, sir.
previous this one no only this one is the module 3 only. I did carry look at it. See after this pass and generate we have this carry select adder.
Okay, sir.
Last class I was just no then carry skip adder was there.
Hmm.
In this class I did this much only. Look at adder only I did.
Okay, sir.
Then I started with this module. In the subsystem, I explained about this one architectural issues. I think I did. These are architectural issues I did. Now I'm asking you people, what is this circuit? This gate? I want to
That's
know
end diffusion.
the end diffusion. I'm talking about this gate. The resolution is not good. Yes, anyone? Others? What is this gate?
So this is enhancement type N.
Enhance.
Oh,
Depletion
say no.
type.
What is your name?
Depletion
Who is this? Who told that depletion? Who told depletion mode transistor?
Sir, Divya.
There's a depletion mode transistor, guys. Oh. Enhancement mode transistor is this where you don't no channel won't be there. You need to give minimum threshold voltage to turn on, right? This is the depletion mode transistor. You see the channel is already formed. This it is a dark. This one is there, right? This is the channel. You see like this. The channel is already formed during the fabrication. This is your this one. This is normal transistor, the enhancement mode transistor. So you should be careful. These are all basics. I told you right. So that's what I told you. Like only few students have joined now around 8:35. So I told them to get into some VLSI core companies. This is must. Fresh graduates are not skilled or industry ready. Need to be strong in CMOS and digital fundamentals. This is very important. That's why you see, you go to any college in Bangalore or even in Karnataka, except BMS RV, not many core companies will come. Intel won't directly go there. They will offer internship now. So these things are based. You should know. This is a NMOS inverter. We'll be using depletion mode transistor where gate is connected to source, and from the source end only is taken output. This is a depletion mode transistor. This depletion mode transistor always it is on. So gate is connected to source. Always it will be operating in linear region, and your channel is always conducting. So when I make Vin is equal to 0, this transistor is off. Vin is 0. This transistor is off. As PMOS is already turned on, so this load capacitor will be charging. This is the ground. This load capacitor will charge and I'll get logic 1 at the output. Logic 1 at the output. This is logic 1. When V in is 0, sorry, when V in is 1, when V in is 1, when V in is 1, now what will happen? Even though it is charging, this transistor is turned on, this transistor is also turned on. It will try to discharge your charges which is there in your capacitor and you'll get logic 0. So tell me, like anyone can tell me how you'll get logic 0 even though this transistor is also on, this transistor is also on. So how you'll get logic 0 on the output? Since it's an inverter, obviously now when V in is 1, your output should be 0 only, right? So can someone tell me what changes I need to do in the circuit? You can unmute yourself and you can tell me. Yes? Anyone? What changes I need to do? You understood my question? Okay, no, I'll come back to CMOS. In CMOS, when V in is 1, so I'll take 0. When V in is 0, your PMOS is on, NMOS is off. This is equivalent circuit, so I'll go for this one. This is PMOS and NMOS where bubble is there. Then it'll be easy. When V in is 0, PMOS is on and NMOS is off. So there will be load capacitor. I'll take this capacitor over here. Sorry. So this is a load capacitor. So your capacitor will charge and I'll get logic 1 at the output, correct? When V in is 0, I'm getting logic 1. Now I'll make V in is equal to 1. I'll make V in is equal to 1. If I make V in is equal to 1, your PMOS is off and NMOS is on, correct? Now what will happen? Your VDD won't charge. So this capacitor, there is no path. So that's why your PMOS is off, but your NMOS is on. Since your NMOS is on, it will discharge. It will discharge and I'll get logic 0, right? This is your normal inverter. Now tell me, same thing for NMOS. How it will be? Even though here I told you, this is a depletion mode transistor where depletion mode transistor always is on. Now when I make V in is equal to 1, your depletion mode transistor is also on. This enhancement mode transistor also on. So how you'll get logic 0 at the output? Yes, you need to answer. Someone can explain. Already, sir has told you about these things. Anyone? Already you learned in all these concepts in module 2. So how we will get logic 0 for this NMOS inverter? Anyone? What about this BiCMOS? BiCMOS? Is this BiCMOS? Sir has done anything about BiCMOS? Yes? Hello? Yes, respond. Yes, you people are there?
Yes, sir.
Sir has done BiCMOS.
Yes, sir.
Then people are not able to understand BiCMOS. You people have seen the circuit. You have seen the circuit BiCMOS.
We can't see
What
this.
of?
Sir.
You're not able to see.
Yes, sir. And now we can see. Sir.
Okay, just go through this in the next class. You need to tell me, how this NMOS inverter works. What changes I need to make so that like I'll get when mean is 1, how I'll get logic 0 the output. So that is your assignment. You need to analyze. Just analyze and you can tell me in the next class. Okay.
Okay, sir.
Okay.